Welcome to Natural Maths, and today we'll be taking a look at an interesting inequality. Let x, y, z be positive real numbers such that x plus y plus z equals to 1. Prove that x cubed over x plus y times x plus z plus y cubed over y plus x times x plus z cubed over z plus x plus z plus y is larger or equals to 1 over 4. Before moving on, don't forget to give a like and subscribe to the channel. Now let's start. So the first thing I want you to think of is these two expressions in a plus b over 2 and the square root of ab, where both a and b are positive real numbers. And which of these expressions is larger? And the answer is b plus b over 2. But why? So when we want to prove a number is larger than the other number, we can actually either subtract them or divide them. This is the two most common ways, and in this case, we will subtract them. Therefore, subtracting them gives us a minus 2 times the square root of ab plus b over 2. And when we think of things that are larger than or equal to 0, and the first thing that comes to mind may be positive integers, or perfect squares, and in this case, we'll be using perfect squares. And consider a into the root squared of root a, and consider negative 2 square root of ab into 2 times the square root of a times the square root of b plus the square root of b squared over 2. And this is simply root a minus root b squared over 2, which is larger or equals to 0. So now, I want you to consider these numbers, a1, a2, all the way up to an, where n is a positive integer, of course, larger or equals to 2. And these numbers are all positive real numbers. And I want you to think of this expression, a1 plus a2 plus all the way up to an over n, and it's nth square root of a1, a2 all the way up to an. And which one of these is larger? And you've guessed this is a1 plus a2 all the way to an over n. But why? So actually here we can use a simple tool called mathematical induction. Let Pn be our inequality. First of all, P2, the base case, is simply a1 plus a2 over 2. And it's larger than a1, the square root of a1, a2, which we've proved above. And let's assume for some n equals to k, Pn holds. Consider n equals to k plus 1. Therefore, we will have a1 plus a2 plus all the way up to ak plus 1. And since we want to make use of the fact that a1 plus a2 plus all the way up to ak over k is larger or equals to the kth root of a1 times a2 times all the way up to ak, so we can actually divide these two pillars into a1 plus a2 plus all the way up to ak and ak plus 1. But since ak plus 1 itself doesn't really do a lot of things, so we can actually add other terms, such as gk plus 1. And here let's define gn equals to the nth roots of a1 times all the way up to an. And here we will add all the way up to gk plus 1, and this will be k minus 1 times gk plus 1. And since we add these terms, we actually need to subtract them, and we will have k minus 1 times gk plus 1. And now, since we know that for a fact we have the AMGM equalities, and we can actually, this is larger or equals to k, which is our assumption, times all the way up to ak plus k times the square root of kth roots of ak plus 1, gk plus 1 to the power k minus 1, minus k minus 1 times gk plus 1. And we can take the common factor out. We will have k a1 all over 2ak plus this kth root of ak plus 1 gk minus 1 plus 1 minus k minus 1 gk plus 1. And applying our assumption on these two variables, we will have this is larger or equals to 2k times the 2kth root of a1 times all the way up to ak plus 1 times gk plus 1 k minus 1 minus k minus 1 gk plus 1. And this expression is actually equals to 2k times the 2kth root of gk plus 1 to the power k plus 1 times gk minus 1 k plus 1 minus k minus 1 gk plus 1. And this expression is equals to 2k, the 2kth root of 2k gk plus 1 minus k minus 1 gk plus 1, and it gives our final answer, which is k plus 1 over times gk plus 1. And we can actually, here we successfully prove that a1 plus all the way up to ak plus 1 over k plus 1, which actually denotes as ak plus 1, is larger or equals to the k plus 1 root of a1 times all the way up to ak plus 1, and which is also gk plus 1. Therefore, we've proved that pk, since pk holds for k plus 1, pn holds for all positive integer n. Smaller case n in this case. And we've successfully proved the AMG inequality. And you might be wondering, what is the AMG inequality? And it's actually just simply this. And this funny little expression is extremely useful in proving inequalities, and is one of the most fundamental inequalities in maths. Back to this question. And since we know for facts that x plus y plus z equals to 1, and we can make use of inequality the AMG, and we've just proved it for. And here, consider x cubed over x plus y times x plus z plus x plus y over 8, since we know these denominators actually looked very annoying, and we want to use the AMG to cancel them out. And since if you're familiar with it, and this will be simply larger or equals to 3 times the cube root of x cubed over 64, which is simply equals to 3x over 4. And we can actually safely say that, similarly, the notation of x cubed over x plus y, x plus z, plus x plus y over 8, plus x plus z over 8 is equals to 3 x plus y times x plus y plus z over 4, and we know this equals to 1, and this simply equals to 3 and 4. And we also know that this expression is equals to 4 times x plus y plus z over 8, and is equals to 4 over 8 plus equals to 1 over 2. Therefore, this expression, which is what we want to prove here, is larger or equals to 4 over 3 minus 2 over 1, which is 4 over 3 minus 4 over 2 is equals to 4 over 1. And when x equals to y z, the inequality holds. And we've successfully proved that inequality x cubed over x plus y times x plus z, plus y cubed over y plus y x plus times y plus z cubed over z plus x times z plus y is largely equals to 1/4 using energy inequality and the fact that x plus y plus z equals to 1. I hope you've enjoyed the video, and as always, until next time.